There is this persistent myth in medicine.
Oh, yeah?
Yeah, that a tumor is just a rogue lump of tissue, right? Just sort of sitting there in the dark, waiting for a scan to find it, or I guess a surgeon to cut it out.
Right, like a static object.
Exactly. But what if we completely flip that perspective? What if every single thing a tumor does, like every time it heals from an injury or hides from an immune cell or even fights back against a drug, it's actually broadcasting a real-time, highly detailed status report straight into your bloodstream?
I mean, that is a profound shift in how we understand human biology.
It really is.
We're finally moving away from treating the body like this opaque black box, and instead we're treating it like a dynamically updating ledger.
And we desperately need that ledger, especially for what we're looking at today, which is non-small cell lung cancer, or NSCLC.
Yeah, the big one.
Right. It remains the most common form of lung cancer and a massive driver of cancer mortality globally. And our current gold standard for keeping an eye on high-risk patients is the LDCT, the low-dose computed tomography scan.
Which has its issues.
Huge issues. Let's be honest about the reality of those scans. They give us a notoriously high rate of false positives. They overdiagnose completely harmless nodules, which triggers massive anxiety, invasive biopsies, and of course, you're hitting the patient with cumulative radiation over time.
Yeah, it's just not ideal.
No, we need something way better than a grainy photograph.
Which is exactly the mission of the research we are unpacking in this deep dive.
Yeah.
We are looking at a really landmark 2026 study, and this was conducted in partnership with the Hormel Institute and the University of Minnesota.
An amazing team.
Truly.
Okay.
And they bypassed the physical scans entirely. Instead, they tracked the blood plasma of 56 NSCLC patients across 87 different time points.
Wow, 87 time points.
Yeah, very granular. They were searching the blood for highly specific protein signatures to answer, well, 3 massive clinical questions. First, how does a patient's entire biological system react to the trauma of surgery?
Okay.
Second, can we predict if the cancer is going to return long before a tumor physically reappears on a scan?
The Holy Grail.
Exactly. And third, crucially, can we figure out who will actually benefit from immunotherapy before they even undergo treatment?
I mean, that is an incredibly tall order. And to map that out, you have to look at this vast, complex soup of proteins floating in the blood.
Right, plasma proteomics.
Plasma proteomics, exactly. But what I found fascinating is that they didn't just run these samples through a standard lab test. They brought in 2 completely distinct, highly advanced technologies to scan the plasma.
They had to, because, no single tool can see everything. The first platform they used is called SomaScan, and you can think of it like an incredibly wide deep-sea fishing net.
Right, and the mechanism here is brilliant. SomaScan uses something called aptamer technology. So instead of relying on standard antibodies, aptamers are basically short, single-stranded pieces of DNA or RNA.
Which is so clever.
It is. Because of their specific sequence, they fold into these highly complex 3-dimensional shapes. They act like custom fit locks that bind perfectly to very specific target proteins.
And they use thousands of them.
Yeah, by using thousands of these different aptamers, the SomaScan can detect a staggering 7,596 different proteins in just a single drop of plasma.
It gives us this massive panoramic view of the body's overall metabolism and structural remodeling. It's an unprecedented level of breadth.
If there is a catch, right?
Right, because while SomaScan gives you the wide view, some proteins, especially those related to cancer and inflammation, are so incredibly scarce in the blood that they just slip right through that net.
Or too tiny or too rare.
Exactly. So they layered a second technology on top of it called NULISA. Think of NULISA as a highly targeted, ultra-sensitive radar designed to hunt down 250 very specific inflammation-related markers.
And NULISA achieves what's called attomolar sensitivity.
Which is mind-blowing.
Just to ground that for you listening, we are talking about detecting a few individual molecules swimming in a sea of billions. The way it pulls that off is through this dual antibody sandwich approach mixed with DNA barcoding. So you basically need 2 separate antibodies to find and bind to the exact same target protein.
Right, like a molecular handshake.
Yeah, and only when both antibodies lock on do their attached DNA barcodes link up to create a readable signal. It virtually eliminates false positives.
Precisely. You have the ultimate wide lens from SomaScan, combined with the ultimate microscope from NULISA.
So what did they find when they pointed these tools at the patients?
Well, the first thing they looked at was the physiological earthquake of surgery.
Yeah.
When a surgeon resects a lung tumor, they aren't just removing a localized mass,
Right.
They are triggering a massive shift in the body's entire chemical landscape. By comparing blood samples taken right before surgery to those taken 2 to 4 weeks post-surgery, the algorithms revealed exactly how the body pivots.
And one of the most striking drops they saw was in a protein called IL-36G, or interleukin-36 gamma.
Yeah, that was a big one.
It is a pro-inflammatory cytokine. Now, my initial instinct was that this felt totally backwards. IL-36G is an immune-boosting protein, right? It activates T cells.
That's right.
So if the body has just been literally cut open to remove a tumor, shouldn't the immune system be screaming on high alert? Why does this critical immune booster just plummet?
It does seem counterintuitive until you look at the tumor as a chronic systemic stressor rather than an acute infection.
Okay, walk me through that.
So think of IL-36G not as a standard wound healing protein, but as the body's systemic fire alarm.
A fire alarm, okay.
While that tumor is growing inside the lung, it is constantly agitating the surrounding tissue. The alarm is blaring 24/7, driving this state of widespread chronic inflammation as the body tries to fight off a heavily entrenched invader.
So it's basically exhausting the system.
Totally exhausting it.
So when the surgeon physically extracts that tumor, the core source of the agitation is gone. The massive drop in IL-36G is basically the sound of the biological sirens finally turning off.
Exactly. The systemic fire is out. But, while the inflammation drops, other markers spike.
Right, like MUC16.
Yes, MUC16. It's a heavy epithelial glycoprotein, and its levels actually increased in the weeks following surgery.
Which, again, sounds alarming because MUC16 is often associated with tumor cells. But here, the biology tells a story of recovery.
How so?
Well, MUC16 is deeply involved in the mucosal barriers of your lung's epithelial cells. When a surgeon slices through lung tissue, there is massive cellular disruption. That post-surgical increase is essentially the chemical debris of the lungs actively trying to repair their mucosal lining.
That makes perfect sense. We also see this massive shift in the proteins responsible for maintaining the extracellular matrix.
The physical scaffolding that holds our cells together.
Exactly. Before the surgery, the researchers saw elevated levels of proteins like CLEC3b and TGFBI. But post-surgery, those plummeted, while completely different scaffolding proteins like SHC1 and THBS3 suddenly surged.
I love the mechanics of this because you can visualize it perfectly as a hostile takeover of a construction site.
Oh, I like that analogy.
Right. So while the tumor is in the lung, it acts like a corrupt real estate developer. It brings in its own shady demolition crew.
The CLEC3b and TGFBI.
Exactly. They constantly break down the lung's natural barriers and build this abnormal scaffolding to help the cancer expand. But the moment the surgeon removes the tumor, that corrupt crew is fired. Their protein levels just drop.
And immediately, the legitimate biological wound healing crew clocks in to repair the damage.
Right.
The reason SHC1 and THBS3, which is thrombospondin 3, by the way, surge so dramatically, is because their specific biological job is angiogenesis.
Building healthy new blood vessels.
Yes, building blood vessels and true tissue reconstruction. The plasma is giving us a literal real-time readout of the body switching off tumor maintenance mode and switching on structural repair mode.
That is wild. Okay, so we are about 5 minutes in. Let's do a quick recap of Section 1 for you listeners.
Sounds good.
Bullet 1. LDCT scans are flawed, but blood proteomics offers a dynamic, real-time alternative. Bullet 2. Surgery causes a measurable drop in chronic inflammation, like the IL-36G fire alarm turning off, and triggers structural wound healing proteins like THBS3.
Spot on.
So here's a question for you to think about. Think about a time you had a major physical trauma or surgery. How long did you feel the systemic inflammation lasting? Because your blood proteins were likely mapping that exact recovery timeline.
It's incredible to think about your blood doing that work. But as amazing as that healing process is, there's a dark cloud hanging over this phase of treatment.
Yeah, the recurrence rate.
Right. Even with clear margins and successful tissue repair, the source material notes that 15 to 20% of these non-small cell lung cancer cases will recur. The mass was removed, but microscopic seeds were left behind.
Which brings us to the ultimate question. If those seeds are too small for any scan to detect, can the blood reveal that the cancer is quietly setting the stage to return?
The short answer is yes. The study identified a highly unique plasma fingerprint in patients whose cancer eventually returned. And it essentially came down to a dual failure.
What were the two failures?
Suppressed immune surveillance combined with an overactive metabolic environment.
Okay, let's unpack the immune side first. The patients who later relapsed had significantly lower levels of circulating immune markers, specifically proteins like FCER2.
FCR2 is a critical receptor involved in how immune cells recognize and respond to threats. When you see a systemic drop in a whole cluster of these markers, it tells you that the immune guards are practically asleep at their posts.
So the body isn't fighting back.
Exactly. The systemic environment is immunologically quiet, which offers no resistance to leftover cancer cells.
But the guards falling asleep is really only half the problem, right? The cancer still needs fuel to grow.
It does.
And this is where we see the metabolic adapters. The patients who recurred had elevated circulating levels of growth factors like FGF19 and an extracellular matrix regulator called SPOCK2.
Yeah, those are definitely fuel.
But the most fascinating and initially confusing marker they found was a protein called KIOX7A2L.
Oh, the KIOX7A2L paradox is one of the most brilliant biological insights in this entire study.
It really is, because in older tissue-based studies, if a pathologist biopsied a lung tumor and found high levels of KIOX7A2L inside the tumor tissue itself, it usually meant the patient had a better prognosis.
Right.
But here, looking at the blood plasma, we see the exact opposite. High levels of KIOX7A2L in the blood predict that the cancer is coming back.
It's wild.
How does a protein go from being a sign of hope in the tissue to a harbinger of doom in the bloodstream?
To understand the paradox, you really have to look at what KIOX7A2L actually does. Its biological job is to stabilize mitochondrial respiratory supercomplexes.
Okay, let's break that down.
In plain English, it is a crucial gear in the engine that helps cells burn oxygen to make energy.
Okay, so it's an oxygen-burning engine part.
Right. Now think about the environment deep inside a solid tumor mass. It is highly hypoxic.
Meaning it's starved of oxygen.
Exactly, because the tumor is growing faster than its own blood supply. In that suffocating environment, the cancer cells adapt by shutting down their oxygen-burning engines. They just stop producing KIOX7A2L locally. So low levels in the tissue just mean you have an aggressive hypoxic tumor.
But the plasma isn't the tumor tissue. The plasma reflects the entire superhighway of the body.
Precisely. If you are seeing high circulating levels of KIOX7A2L in the plasma, it means the patient's overall systemic metabolic engine is running incredibly hot.
Wow.
Combine that high metabolic fuel with the suppressed immune profile we just talked about, those sleeping guards, and you have created the perfect systemic greenhouse.
The patient's entire body has basically adapted to a state that is highly favorable for cancer to grow.
Yes.
So we're realizing that cancer recurrence isn't just about a rogue cell quietly dividing. It requires the entire host body to inadvertently roll out the red carpet.
That's a great way to put it.
By reading these low immune markers and high metabolic markers, we can spot the body preparing that environment months before a physical tumor takes shape.
And that leads to a huge realization.
Yeah, it really makes you wonder, if we can read this environment in the blood, could we hypothetically step in with a targeted immune booster to wake up those sleeping guards and alter the environment before the cancer even has a chance to take root?
That is the exact frontier of interception oncology.
Okay, let's do our Section 2 recap. Bullet 1. Cancer recurrence leaves a very specific fingerprint in the blood months before it shows up on a scan.
Yes.
Bullet 2. A suppressed immune profile like low FCER2 and altered metabolism like high KIOX7A2L predict that recurrence.
Perfect.
So here's a question for you listening. If we know the immune guards are falling asleep, could we hypothetically intervene before the recurrence even takes root?
And speaking of intervening with the immune system, we have to talk about how this study approached the puzzle of immunotherapy.
Yes. Section 3. Immune checkpoint inhibitor therapy, or ICI, has been nothing short of a miracle for some lung cancer patients. It fundamentally changed the game by taking the brakes off the patient's own T cells so they can attack the tumor.
But there's a big caveat.
Huge. It only works for a fraction of patients. Until now, figuring out who will respond has been largely guesswork.
To solve this, the researchers focused intensely on the baseline blood samples. These were drawn right before the first drop of immunotherapy was ever administered.
So, looking at the starting line?
Exactly. They wanted to know what the biological landscape looked like before the intervention, comparing those who ultimately responded to the drug against those whose disease aggressively progressed.
And their findings challenge a very common assumption about the immune system.
They really do.
The non-responders, the patients the immunotherapy failed to help, actually had globally higher baseline levels of circulating inflammatory markers compared to the responders.
Higher inflammation.
Yeah, we're talking about a massive cluster of inflammatory mediators like IL-6, CRP, and crucially, a protein called SPP1, which is better known as osteopontin.
It's a completely counterintuitive finding.
Wait, I'm confused, because you would naturally assume that a highly inflamed, highly active immune system would be perfectly primed to attack the cancer once the immunotherapy takes the brakes off.
Right. If the army's already riled up and firing weapons, giving them the green light should result in a massive assault on the tumor.
So why doesn't it?
It sounds logical, but biologically, high baseline inflammation in a cancer patient does not equal a ready immune response. It indicates profound immune dysregulation.
Oh, I see.
It means the environment is toxic, chaotic, and, ironically, highly immunosuppressive.
So instead of an army ready to fight, it's more like an army that has been fighting a brutal losing battle for 5 years. They're completely out of ammunition, deeply confused, and totally exhausted.
That's a perfect way to look at it. Let's look at osteopontin, or SPP1.
Okay.
When a tumor secretes high levels of osteopontin, it actively recruits macrophages, which are a type of white blood cell, to the tumor site.
It's usually a good thing.
Usually. But instead of letting those macrophages eat the cancer, the osteopontin forces them into a subservient state where they actually help the tumor grow and build a dense physical barrier around it. It essentially builds a biological moat.
Oh, wow. So when the immunotherapy drug arrives to take the brakes off the T cells, those T cells are trapped in an exhausted, chaotic moat of inflammation.
Precisely. They physically and chemically cannot mount an attack.
Meanwhile, when they looked at the patients who did respond well to immunotherapy, they found a very different baseline. They had much lower systemic inflammation, but they had higher baseline levels of specific regulatory proteins like IL-24.
And IL-24 acts as a known tumor suppressor.
Right.
Helps regulate cell differentiation and apoptosis, which is programmed cell death. So the responders weren't just less inflamed. Their bodies already had a quiet, functional baseline defense mechanism in place that the immunotherapy could successfully amplify.
This changes everything about how we view treatment failure.
Completely.
Because a high level of baseline inflammation, marked by things like osteopontin and IL-6, isn't a sign of immune strength, it's a signature of exhaustion.
Yes.
Which begs an incredible question. Let's do our Section 3 recap. Bullet 1. High baseline inflammation is actually bad news for immunotherapy response. Bullet 2. Elevated markers like IL-6 and osteopontin indicate a dysregulated, exhausted immune environment, that moat.
Good summary.
So here's the question for you listening. If an inflamed, exhausted environment guarantees immunotherapy will fail, what if we could artificially calm the body's systemic inflammation before administering the drug? Could we use an anti-inflammatory to drain that biological moat and turn a non-responder into a responder?
It is the holy grail of precision oncology. But to even attempt that, we need absolutely bulletproof data on what predicts long-term survival. Which brings us to the most statistically rigorous part of this entire study, the 4-protein survival signature.
Let's get into the math. The researchers wanted to find the ultimate prognostic markers for overall survival under immunotherapy. They ran a massive data set of thousands of proteins through a regularized Cox proportional hazards model.
And what fell out was a very specific 4-protein signature.
And the rule was stark, right?
Very stark. Higher baseline levels of these 4 specific proteins strongly predicted worse overall survival.
The proteins are CEACAM5, PTX3, FGF23, and AR-EDGE. And when you look at what they actually do biologically, you understand exactly why they are a death knell for immunotherapy.
They work together to create an impenetrable fortress of growth and immune evasion.
Let's break down that fortress. First, you have AR-EDGE, or amphiregulin. It's a growth factor that binds to epidermal growth factor receptors. Its entire job is to step on the gas pedal and force epithelial cells to rapidly divide and multiply.
But rapid growth isn't enough, right?
Okay.
The tumor needs to remodel its environment to fit that growth.
Right.
That's where PTX3, or pentraxin-3, comes in. It's released by the surrounding stromal cells in response to inflammation, heavily altering the tissue architecture to accommodate the growing mass.
Making room for it.
Exactly. Then you have FGF23, which is a fibroblast growth factor that alters systemic mineral metabolism to support this massive, rapid cellular expansion.
And finally, you have CEACAM5. This is an oncofetal growth factor, but crucially, it's a cell adhesion molecule.
That's the sticky part.
Yes. As the tumor rapidly multiplies thanks to the aera gas pedal, CEACAM5 provides the stickiness that helps these new cancer cells adhere to surrounding tissues and begin to spread.
It's a brutal combo.
So if a patient walks into the clinic and their blood is saturated with proteins driving rapid division, tissue remodeling, metabolic hijacking, and cellular adhesion, it tells us the tumor is heavily entrenched and the immunotherapy doesn't stand a chance.
The biological synergy is undeniable. But as researchers, whenever you identify a small signature like this from a massive data set, you have to confront a major statistical demon.
I'm so glad you brought this up because anyone listening who works with big data is probably shouting at their device right now.
Oh, absolutely.
They measured nearly 8,000 different proteins in a relatively small group of just 56 patients.
Right.
When you roll the dice 8,000 times on a small sample size, the mathematical reality is that you are practically guaranteed to find patterns and correlations that are complete statistical illusions.
False positives.
Exactly. How do we know these 4 proteins aren't just mathematical noise?
It is the most critical hurdle in bioinformatics today. To prevent these false discoveries, standard statistics just aren't enough. The researchers deployed a highly advanced machine learning algorithm called STABLE, which they paired with adaptive lasso regression.
The mechanism behind STABLE is fascinating because it relies on artificial feature injection.
Explain that one.
I picture it like trying to identify a suspect in a police lineup. If you just have your witness look at a few people, they might pick someone just because they look vaguely familiar. But STABLE algorithmically injects highly realistic but completely fake, noisy data into the data set.
Like decoy proteins.
Yes, decoys. It forces the model to choose between the real biological signals and the fake decoys over and over again.
Exactly. It runs thousands of iterations. If a real protein signature is easily replaced by a fake decoy, the algorithm throws it out as an illusion.
It calls its bluff.
Right. Only the true biological signals that consistently beat the artificial noise iteration after iteration survive the test. The 4 proteins, CEACAM5, PTX3, FGF23, and AEG, beat the decoys every single time.
But they didn't even stop there. Proving it mathematically isn't the same as proving it biologically in a real-world setting.
No, you need independent verification.
So to be absolutely certain, they validated these 4 proteins using a completely different orthogonal platform called NULISA.
And by orthogonal, we mean a technology that uses fundamentally different physics and chemistry to measure the proteins. You don't want to use the same tool twice and risk repeating the same blind spots.
Makes sense.
And ELISA uses flow cytometry and pairs of antibodies bound to spectrally encoded microparticles. It physically counts the proteins in a totally different way.
And crucially, they didn't just test the original 56 patients again. They applied this totally different technology to an independent external cohort of 114 new patients.
And the signature held up perfectly.
Wow.
Those 4 proteins consistently identified the patients who would not survive the immunotherapy. The mathematics were scrubbed by AI, and the biology was validated across multiple platforms and hundreds of patients.
Okay, final recap for Section 4. Bullet 1. Elevated CEACAM5, PTX3, FGF23, and AIR heavily predict poor survival under immunotherapy.
Yep.
Bullet 2. Advanced algorithms like STABLE and third-party testing like NULISA proved these findings are biologically real, not just statistical noise.
What?
So here's a question for you. With tools combining AI-level statistical scrubbing and attomolar protein sensitivity, we're no longer guessing. Do you think you'd want to know your exact odds before choosing a grueling treatment?
It leaves us with a reality that is both empowering and immensely heavy. We are moving into an era where we can map out a patient's precise odds of survival based on the unique chemical dialogue happening inside their blood.
It fundamentally changes how we think about informed consent and treatment choices.
It really does.
If you could see the mathematical certainty that your exhausted immune system couldn't handle the therapy, you could choose to focus on entirely different clinical trials or quality of life measures rather than fighting a losing battle blindly.
And that is the true synthesis of this entire deep dive. This isn't just a story about non-small cell lung cancer or complex laboratory techniques. It is a story about the blood acting as a living, breathing diagnostic ledger.
Every single action the tumor takes is recorded.
Exactly. Every time the tumor's demolition crew clocks out, every time the cancer hides in hypoxia to alter its metabolism, every time the immune system becomes trapped in an inflammatory moat, it leaves an undeniable receipt in the plasma.
We've spent decades treating cancer by taking snapshots every few months and praying the tumor shrinks. But if a single drop of blood can reveal the exact molecular strategy a tumor is deploying today, it forces us to ask a really profound question.
What's that?
How long until we stop using this technology merely to predict the future? How long until we use these real-time ledgers to dynamically alter a patient's drug cocktail on a Tuesday simply because of what the tumor whispered to the blood on a Monday?
We are standing on the edge of a world where we can outsmart the cancer in real time, matching its every move before a scan ever catches it.
It is a profound and hopeful shift in the war on cancer. Thank you for joining us as we unpack the mechanisms, the math, and the future of plasma proteomics. Keep asking the hard questions, keep looking for the biological why, and we will catch you on the next deep dive.